Hi, today I will talk about polynomials again. I will continue with the polynomials. Okay, last time we stopped, we finished here in this definition. Let me finish that definition. So let R be a commutative ring with 1, and let this A0, A1, let me A1x plus A2x squared, blah, 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 an x to the n be a polynomial. Be a polynomial. Of course, we always assume that an is not 0. Be a polynomial. And for r in R, let's define, we define f of r to be, so we just replace x by r, so it is a0 plus a1 r plus an r to the n. And if f of r is equal to 0, if f of r is equal to 0 in the ring R, then we say that R is a root of f, or a 0 of r, 0 of f, either one. And let's give some example. As the first example, let's consider the ring of integers. And let's take f of x to be x squared plus 1. In this case, f of 1 is 1 squared plus 1 is equal to 2. So that 1 is not a 0 if 1 is not a 0 of f. In particular, also, as we know, this polynomial has no zeros in real numbers. And in fact, this f of x equal to x squared plus 1 has no zeros. Zeros in Z, or even in R. And the second example. So let's say, let's take in R. Let's take g of x to be x squared minus 1. Then g of 1 is 0. G of minus 1 is also 0. So that it has two roots. It has two roots. So 1 and minus 1 are two roots. The question, is there any other root? Of course, as we know, there is no other root, and we will prove it in shortly. The reason is that this f of this z is an integral domain. So, but let's look at as a second example. Let's take r to be z6 or z2, for example, so that oops. Yeah. Then if we take f of x to be again x squared plus 1, then this f of 0 is 1, so that 0 is not a 0, so the 0 is not a root of f of x in Z2. And if you look at f of 1 is 1 squared plus 1 in Z2. This is 0, so that 1 is a root of f. Okay. So here's the definition. definition. Let R be a commutative ring with 1. Commutative ring with 1, so that it has multiplicative identity, and let f of x and g of x be two polynomials in over R, such that g of x is not 0. So it is not a 0 polynomial. We say that g of x divides f of x, and write like this: g of x divides f of x if there is a polynomial, there exists a polynomial q of x in R of x, such that f of x can be written as q of x times g of x. So in this case, we also say that so it either g divides f, as we wrote above, or g is a factor of f. G of x is a factor of f, just like in the integer case. Okay. So here's a theorem, remainder theorem. Remainder theorem. So let R be a commutative ring with 1. Commutative ring with 1. F of x is a polynomial over R, so that coefficients are from R, and let's say A is an number, A is an element of R. Then there exists a polynomial qx in R of x, such that we can write f of x as q of x times g of x plus f of a. And f of a is a constant term, of course. Here's a proof. So if we apply the division algorithm, by division algorithm, that we proved in the previous lecture, we can write by taking for g of x, if you take g of x to be, oops, that's not g of x, this is x minus a. Sorry. Yeah, here it's x minus a. There is no g of x in the theorem. So in the previous, in the division algorithm, let's take for g of x to be x minus a. Then there's a polynomial, unique polynomial, Q of x in R of x such that, and also Rx such that f of x is equal to Q of x times G of x. G of x is x minus a plus R of x. Here the degree of R is less than the degree of x minus a, which is 1. So that degree of x minus a, degree of R is either 0 or so that degree of R, there's only possibility is either minus infinity or degree of R is 0. If degree of R is minus infinity, then R is equal to minus infinity. Then R is equal to 0, okay, R is equal to 0. Well, in any case, if degree of R is 0, degree of R of x is 0, then R is constant. So in any case, f of x is equal to Q of x times x minus a plus R, where R is constant. R is from the ring R. Then if you evaluate this at f of a, it is Q of a times a minus a plus R, but this is a minus a, this is 0, so that the result is R. So that means R is equal to, so thus R is equal to f of a. So if we replace that here, we get f of x is equal to Q of x times x minus a plus f of a as required. Okay, that's the proof of the remainder theorem. Okay, next, what do we do? What do we have? Oh, let's see. So here's the corollary of this above theorem. Corollary. Let R be a commutative ring with 1. Let R be a commutative ring with 1. And A is an element in R. F of x is a polynomial over R. Then x minus a divides f of x if and only if f of a is equal to 0. So it follows directly from the above theorem, which I will not write explicitly. So let's look at this example again. One more example. As we looked above, remember f of x is equal to x squared plus 1, for example, has no root in R, and it has 2 roots over z, and it has f of x, it has 2 roots in C. So namely, the roots are plus or minus I. So as we know that any polynomial over the complex number or real numbers has at most n roots. But let's consider this example, second example. Let's take R to be z8, namely this is z over 8 times z. So this is in some sense the classes of these 1 and 7. Let's write it like that. So we consider the additional multiplication by modulo 8. So let's look at the consider f of x is equal to x squared minus 1. And in the integers, it has only two solutions, plus or minus 1. But let's look at over this integer, over this ring Z8. Well, let's look at f of 0. F of 0 is 0 squared minus 1, which is 7 minus 1. And f of 1 is 1 squared minus 1 is 0. And f of 2 is 2 squared minus 1 is 3. F of 3 is 3 squared minus 1, which is 8. That's 0. And f of 4, let me write here. F of 4, 4 squared minus 1, which is 15. In modulo 8, it is 7. And f of 5, in Z, we are looking, remember, in Z8. F of 5 is 5 squared minus 1. It is 25, 24. 24 is 3 times 8, so that's equal to 0. And F6 is equal to 6 squared minus 1 is 35, which is 3. And F of 7, by the way, it is 7 squared minus 1 is 48. 48 is equal to 0 in the string. So therefore, this x squared minus 1 has 4 roots. Has 4 roots. So it's of degree 2, but it has 4 roots in Z8. Namely, these roots are 1, 3, 5, and 7. These are the roots of this polynomial. But so that it has degree 2 and it has 4 roots, but this cannot happen, as we will prove now. This cannot happen over if R is an integral domain. In this case, of course, this Z8 is not an integral domain because 4 times 2 is 0, so that it has 0 divisors. It's a quantitative ring with 1, but not an integral domain, right? Note 2 times 4, let me write like this. 2 times 4 is 0 in Z8, so that Z8 has 0 divisors. So that it's not an integral domain. It is not an integral domain. So our next theorem is, so let R be an integral domain. Now, before we always had was the quantitative with 1. Now there is also, we also assume that it has no 0 divisors, so that's an integral domain. Let R be an integral domain, and f of x is a non-zero polynomial. Be a polynomial. Polynomial of degree n in R of x. Then there is f of x has at most n roots in R. So it cannot be more than, it need not be n roots, but it has at most n roots. Here's a proof. So if degree of f is equal to 0, degree of f of x is equal to 0, then f of x is equal to some constant, where c is constant. And since we assume that it is not 0, c is not 0. In this case, f of x has no roots. So the number of roots is 0, which is that's equal to the degree of the polynomial, which is equal to, so the number of roots is equal to the degree of f of x, which is 0. Okay. Now suppose that, assume that n is equal to 1, greater than or equal to 1, and the theorem is true for polynomials of degree less than or equal to 10, or less degree n minus 1. Okay. Okay. Now, and let now f of x has degree n, have degree n, n is greater than or equal to 1. And if f has no roots, if f has no roots, then we are done. So the number of roots is 0, and that's less than the degree of n, degree of f, which is n, degree of f. 0 is the number of roots. And suppose that f of x, it has a root. So suppose, so f of a is equal to 0 for some a in R. Then by the above theorem, we can write f of x to be x minus a times qx. Or by the above theorem, f of a is equal to 0 in this case, and the degree of so in this case, since we are in the integral domain, degree of q of x is n minus 1. So if f of r is equal to 0 for some r, then what do we have? R minus a times q of r is equal to 0. Q of r is equal to 0. So if a is not equal to 0, if r is not equal to a, then so we have this qr. So we can, this is not 0. So r of r minus a is not 0. So since we are in the integral domain, we have that qr is equal to 0. So the all roots of f of x are either a or the roots of q of x minus 1. But q of x, qx has at most n minus 1 roots. So by induction, qx has at most, so that r is a root. Here is a root of q. So by induction, our q of x has at most n roots, n minus 1, sorry. And when we include this a to these roots, we have at most n roots of f. So therefore, f of x has at most n roots as claimed. Okay. Next. Now, let's now talk about the algebraicity over a ring. So here's a definition. So let R be a commutative ring. Let R and S be commutative rings. Commutative rings with R is inside S. think it like R is equal to, let's say, rational numbers, C is equal to complex numbers, or R is equal to Z, S is equal to R, for example, real numbers. And assume that the one of complete the rings with also with 1, and okay, also with the identity of 1 is equal to identity of S, suppose. Remember, the identity of a subring need not be the identity of the bigger ring. Okay, an element, in this case, we say that an element A in S in the bigger ring is said to be called algebraic over R if there is a polynomial there's a non-zero polynomial, not only polynomial, non-zero polynomial. Non-zero polynomial f of x in the over R such that f of a is equal to 0. If R is not algebraic, of course, R is equal to S, then everything is algebraic by this definition. So if A in S is not algebraic for R, then we say that it is said to be transcendental. So remember transcendental functions, transcendental over R. So this transcendental. So here is an example. So first example is, let's take R to be Z, S to be real numbers, and the square root of 2 is an element of real numbers. This is algebraic. Square root of 2 is algebraic over Z. The reason is that if you take f of x equal to x squared minus 2, then f of, so that all the coefficients of x squared minus 2 are from integers, and f of square root of 2 is 0. So therefore, square root of 2 is algebraic over Z. Square root of 2 is algebraic over Z. And second, that if you look at pi and the and I, E, the number E, then these are transcendental over Z. So these are real numbers. Pi and E are real numbers, but there is no polynomial with integer coefficients such that it is 0 is pi or E. And we will not prove this. The proof is outside of the scope of this lecture. And the third statement is, if you look at the transcendental number, this algebraic number square root of 2, and square root of 3 is also algebraic, and over Z. Let's show that this is algebraic over Z. Algebraic over Z. So we need to find a polynomial whose root is one of its root is square of 2 plus square root of 3. For this, so I will do like this. So suppose this is a is equal to square root of 2 times square root of 3. Then if you take the square of both sides, it is 2 plus 2 square root of 6 plus 3, or a squared minus 5 is 2 square root of 6. And if you take the square of both sides once again, if you square both sides once again, we have a to the 4 minus 10a squared plus 25 is equal to, the other side is 4 times 6, 24. So when we subtract it, it is so that we have a to the 4 minus 10a squared plus 1 is equal to 0. So if f of x is x to the 4 minus 10x squared plus 1, this is in zx. And f of square root of 2 plus square root of 3, which I urge you to check this is equal to 0. So therefore, square root of 2 plus square root of 3 is algebraic over z. And I urge you to show that. So here's the exercise. Show that, for example, square root of 2 minus square root of 5 is algebraic. Even third root of 1 over 2 minus square root of 5 is algebraic. So you should do this. These are algebraic numbers. Okay, or also 2 to the third root of 2 times 5 to the 1 over 2, for example. This is also algebraic. So I will leave this to you as an exercise. Okay. Next. So here's the definition. Once again. So if R is an integral domain, then Rx is also integral domain, so that we can consider it as field of fractions. So and then the field of fractions, and the field of fractions or quotient field of fractions of the integral domain, field of fractions of the integral domain R of x is called the field of rational functions. Rational functions over R, and it is denoted by exactly R of x, but we write this these parentheses, R of x, so that R of x is f of x over g of x's, where g of x, f of x, and g of x are polynomials over R of x, and we need to assume that this g of x is not a zero polynomial. Remember the definition of the construction of the field of fractions. Okay. Now, okay, this is the let's see how much time do I have? 5 minutes. Okay, perhaps it's a good time to stop here. Then I will continue with let me write the title of the next section, next course. It is divisibility. Well, let me write like this: divisibility and factorization. So this will be the title of lecture 12. Okay, have a nice day.